Okay, it's 1:10. We can start. Welcome to week 3 of MLF. Just a show of hands before we begin. How many of you are first year students? Oh, gotcha. And how many of you have heard about the term neural networks? Okay, good. So um, today we'll be hopefully have like a gentle introduction into the concept of neural networks. Neural networks is at the fundamental concept. It's a foundation of a lot of the deep learning um, architecture. What deep learning is, it's your object detection, your speech recognition, your modern large language models, and then most recently with Sora 2 coming out, you know, with video generation. And all of these higher level, more complex systems all rely on neural networks. Okay. Now, the astute among you might have realized that, hey, this is a neural networks part 1. Is there a neural networks part 2? And yes, there is a neural networks part 2, and that's next week. So when you take a neural networks course, or when people teach neural networks, it's typically split into 2 lectures or 2 days. The first day, more or less, we'll be talking about terminology. How do you go about building, this model? What's the math behind this model? That'll be today. Everything today will assume, or all the neural networks we're using today will assume that it's already trained. Okay, it's the best model that there is. We don't know how we train it, but it's already trained. And then next week, we'll be talking about, how do you go about actually training it? What's back propagation? What does that mean? But yes. Now, throughout this lecture, I'll be including a lot of visuals to show what's happening in the hidden layers of the neural network. Is this the correct way of thinking? Like, are you always able to see what's happening in the hidden layers? No. I think the right way to go about thinking what's happening in a neural network is, I don't know. It just works. That's the right way of thinking about it, and that's what most people at these large companies like OpenAI, there's like, oh, okay, it works. Do we know what's happening inside? Not really, but like, it gets what we want. And there's like an active research field in trying to understand what's happening internally. But that's the point. So we'll go over just a breakdown of the content for today. We'll go over a brief recap of week 1 and 2, the material that's been taught then. We'll try and motivate why we need different machine learning models besides linear and logistic regression, with some limitations of linear models. And then we'll talk about the structure, definitions, terminology for neural networks, and ultimately end with why you should care about neural networks. Okay. So in week 1, for linear regression, you should have learned about linear regression. Your model equation here is just some weight times your input, and then you have some bias. The whole point about regression is you want to find some relationship inside your data set. So for linear regression, we're assuming some linear relationship between our input and our output, and we're fitting some line of best fit with this purple graph. And then to quantify how well our model is doing at fitting, we have this mean squared error that basically calculates the distance between our predicted value and our actual values. Okay. And then in week 2, you should have learned about logistic regression. Again, we have our vectorized format here, which is our weighted sum, our weight times our input plus some bias, and it's wrapped around a sigmoid function. And the whole purpose about logistic regression is that it's able to classify 2 data points, or 2 classes from each other. And the line that separates those 2 classes is called a decision boundary. And last week, you should have also learned about the cross entropy loss, and why the cross entropy loss has a specific formula with issues with the mean squared error loss and the threshold loss. So I guess to start off, what are the trade-offs with logistic regression? What are some underlying assumptions about the data when we choose the logistic regression model to classify our data points? What do we see? When I say what do we see, I'll say what do we see throughout this whole lecture. So when I say that, it should be a Pavlovian response where I want some of you guys to raise your hands and tell me what you guys see. So what do we see? Yeah.
We see only two classes, unfortunately, more.
Yeah.
I assume to be like linearly distinguished by a point.
Yeah. So logistic regression, the assumptions we make are that there is a linearly separable data set. So we can draw a line or a plane that separates our two data sets or two classes. But the example on the right, obviously, a line is not represented, or a line is not does not correctly represent our decision boundary. Okay. So for logistic regression, a lot of the advantages of this model is that it's very simple and it's very easy to train. It's also very easy to understand what's happening here. But as you've correctly pointed out, you can't do multi-class classification. If you have more than 3 classes, you can't draw more than 3 lines. There's only 1 line. And the other thing is, if it's not a line that separates our 2 classes, then logistic regression fails there. Now, when you take a machine learning course, this is probably how they motivate it with the XOR function. The main point I want to show is that the graph on the left, if you look at or the right, here, but graph on the left. If you look at it, there's no decision boundary or linear decision boundary that separates it cleanly. You can't just cut a line through it and have all positives on one side and all negatives on one side. But we can do something called feature mapping, where given your x1, x2 inputs, you can map it out to the 3-dimensional space. And after mapping out to the 3-dimensional space, it is linearly separable. Now, the issues with this is that, how do you figure out how do you calculate that 3rd dimension? Here you can just multiply x1 and x2, but is that obvious? I don't think so. And so designing these feature maps so that it is linearly separable is hard. And the whole purpose of these neural networks is that they can learn these feature maps on their own, and we don't have to do anything. We don't have to, think about how to come up with this. So to ground ourselves in examples, I've included 2 data sets, more or less, for this lecture. The first data set is a spiral data set with 2 classes, red and blue. Okay, our objective is, how can we make this linearly separable in the end? And the other objective is, how can we draw our decision boundary? Now, when we look at this notation here, you'll often see these notations in papers. Well, what do you think this? Oops. What do we think these indexes are indicating to us? Yeah.
Sounds like the index of the data points within the broader data set.
Yeah, that's correct. So that would be just a specific, like that index indicates a specific data point in our data set. So x of I could be this dot, could be this dot. Okay. This is just all notational. Okay. Now, for neural networks, I think we always like to give analogies. So the neural network is our attempt at making the human brain. And the fundamental unit for a neural network is, or at least for the brain, it's a neuron, right? Now, I'm not a biologist, so I don't really know these terms. The main thing is that these dendrites here in the brain these dendrites here receive some input, some information. Our cell body determines what information is important and then sends out some signal or sends out some output signal through our terminal. And these terminals are then can be connected to other neurons, to form like a memory or to see that that the shirt you're wearing is green. Okay. Now, in a similar sense, the neurons of the neural network or our nodes take in some input. Okay. Determine what input is important. Then our activation function determines what information should be sent out to other nodes or to just be sent out to our output. Okay, and the first part, there's two key parts. The first part of the node is our weighted sum, and the second part is our activation function. So we'll first look at this weighted sum. So graphically, we can represent our nodes as circles. For now, I just want you to think about these nodes as a way to store numbers. Okay, and mathematically, we can represent the stacks of nodes as a vector where the number of nodes equals to the number of rows. So because we have 3 nodes here, the main important part is that the vector here has 3 rows, or this three number here. And I'll talk more about what these numbers represent later. Now, for our weights and biases, if the nodes represents the circles, our weights are represented by the edges. And then in some papers, you'll see that these biases are connected to, or you might have like a small node at the end that's connected to our output node, and that would be your bias. One way to understand our weights is it's a way to measure how important each piece of information is that's coming into this incoming node. Okay. And then the other way, or for biases, it's how to offset the importance of information. So there might be instances where weights are very small, and you still want to send out some information to your other nodes, in which case you can just set your bias to be very high. Yes. And then the main thing is that it's a weighted sum. Okay, you multiply the weight by the incoming node, by the previous node, and then add it all up in the output node. So just to get the brain, warmed up again, what would question mark here be? What value would the question mark be here? You multiply your weight by the previous node, and you add all up in the output node. Yeah, 1.5. Why? Because you're multiplying W1 by 0, which is 0, W2 by 1, which is 0.5, W3 by 0.5, which is 0, and then you add up your bias, which is 1.5. Okay. And just to get another example, we're adding some more variables here. What would the output node here be? And you guys can discuss among yourselves. I'll give you guys, I don't know, a minute or 2 minutes, 2 minutes. Okay, maybe 2 minutes was too long then. All right, well, what's the answer here? Does anyone want to answer? Yeah.
So if we add W1 and X1, X2, W2, and then X3, W3, W.
Yeah, that's correct. It's a weighted sum. Okay, it's very, very simple. You just multiply your weight by your input or corresponding input, and you add them all up. Okay. Now, visually, we can represent it in 2 dimensions. One way to think about what your weights are doing is it's stretching and shrinking your scale, your x-axis or y-axis. So we have our spiral data set here. What our weights are really doing is it's pulling our x-axis or shrinking our y-axis. But it doesn't make it linearly separable, right? And that's why we need the activation function. Now, the activation function, it decides what information to send out to other nodes or other neurons. You also hear that it provides non-linearity to our neural networks. It allows the neural networks to be powerful. These are all like phrases that people say when we talk about activation functions. The math, the function itself can be any non-linear, non-polynomial function. So, what's your favorite function? Any.
Cosine.
Yeah, cosine is one. What's your favorite function?
Squared.
X squared, maybe non-polynomial. Non-polynomial.
Like a little.
Yeah, it can't be x squared, x cubed. It can't. Yeah, sine x. Okay. And then when we apply this activation function, it's always element-wise application. What does that mean? Let's say we have this matrix. Okay. The key thing is that the matrix is defined. It's just a way to format your numbers, where you have some number of rows, the number of columns. The number of rows, this first number here represents the number of rows for your matrix. And this second number here represents the number of columns in your matrix. And the element itself is determined by this ij number, where I is your row number and j is your column number. So as an example, x11 would be row 1, column 1. And this would be the 1, 1 element. And this would be row 2, column 1. Okay. Now, when we say element-wise, we say that when we apply this activation function to this matrix, we apply it to every single number or thing stored in this matrix. Okay. That's what we mean by element-wise. Now, the reason why I say that activation functions are what make neural networks powerful, if we look at this GIF for a second, okay, we have our initial spiral, we're stretching it, and we're squeezing it, and we're stretching it again, and we're squeezing it, until we get this final state where we can just draw a linear line, or a line that separates the two classes. Now, does this, I guess this equation remind you of anything from previous weeks? What do we see? Yeah.
Kind of looks like the linear regressions we did before, just with the transformation of words.
Yeah. It is similar to the linear regression. It's similar to logistic regression, where our activation function here is just a sigmoid function. Okay. Also, notationally, you might see it in this form where Z is called our pre-activations. Z is just a weighted sum, and then your activations is 5Z. Yeah.
So for the activation function, we choose any nonlinear function and it works.
Yes. But any nonlinear, non-polynomial function works. Yeah.
Just a comment about that. So someone brought up, or two people brought up sinusoidal functions. Those can be linearly decomposed. Does that not cause the issues?
Can be linearly decomposed.
Taylor series power or
Oh, any function can be approximated using or any, I think, continuous function can be approximated by. There are better choices for. What I'm trying to say is sine cosine isn't the best choice. There are specific functions that we use that have been shown that to be make neural networks powerful. I don't think Taylor decomposition matters here, but I might be wrong. The reason why I say any nonlinear non-polynomial. If you take just a very simple function, our identity function, y equals x, and then you make it piecewise where the negative values get sent to 0, this function works. Even, it's a very simple modification, but it works. Okay? As an activation function. Some other examples we have are hard threshold logistic function and then hyperbolic tangent function. Tan H is the one that we will look into today and see what kind of behaviors it causes for our input. So if we look at our tan H activation function, we apply it to some vector xy. Okay, what would I guess first off, how would we apply this activation function to our vector? Yeah.
It produces a tan H of 1000 and tan H of
Yeah. So again, it's element wise. So we do tan H of 1000, tan H of 0.5. Now, approximately, what would the top value be? The tan H of 1000. I don't know if, are you guys able to see this axis?
Yeah,
Okay.
one.
Yeah, one. Okay. So the top value is 1. What is 0.5 approximately if we squint really hard?
0.
Yeah. Huh?
Minus 1.
No, 0.5 would not be -1.
0.5.
Yeah. Well, the main point is if we squint really hard at this tan H function, it's linear, more or less linear. But as you approach maybe very big negative numbers, it approaches -1. As you approach very big positive numbers, it approaches 1. And 1.5. So then if we look at this layer evolution, I know one pretty quick. What do we see? What do we see? What do we see? It's stretching, and then also I have 6 slides, so we get to see this 6 times. But what do we see? What do we see? Yeah. That's one thing. These GIFs, man. We're stretching, and then somehow we've reached this state. We're stretching the space past. Oh, one thing to note, the bounds are 1 and -1 here. Let me just write this down. Okay. Bounds are -1 and 1. So what do we see here? What do we think our tan H activation function is doing? Why? What do we see? I wish I figured out how to make that GIF repeat. Yeah.
It transforms the plane. Where?
Yeah. I would say the way to think about it is, again, your weights are pulling this 2-dimensional grid. Your tan H function, like we said before, for any values that are past 1 and negative, or any values that are past 1 and -1, it brings it back to 1 and -1. So if you see, let's do this slideshow again. If you see this space gets stretched past this 1 and -1 bounds, and then the nonlinearity comes in where any values inside this 1 and -1 bound, it's more or less the same. But all values outside this 1 and -1 bound gets projected back within this grid. Okay, that's what we mean by nonlinearity. Certain regions don't get scaled, other regions do get scaled. If it's linear, then the whole x-axis gets scaled or the whole y-axis gets scaled. Okay. So ultimately, what are nodes? Nodes are
Vectors.
close. Nodes are functions. Nodes are functions of vectors. Nodes are functions. Okay. Does everyone understand this? Again, nodes, weighted sum activation function. Ultimately, they're a function. Okay. If you don't understand this, the next parts will be more confusing. So, no questions from the audience. No questions. Yeah,
Depth and value things that that's one.
this entire thing.
You would call that.
No, I would call this a node, this output a node. I would call the circles the nodes.
Each node is a different function, or it's always the same function?
It's always. I'll answer that question later on. Yeah.
So the input nodes are also like functions.
No, the input nodes would just be okay. Input nodes would be like your input space, like your x variables. They're just x. It's not really a function. All other nodes are functions. So your input nodes are just your inputs. All other nodes are functions of your inputs. Yeah.
Don't the outputs then serve as inputs? Like over
Are what?
doesn't the outputs later serve like inputs or other?
Yes. We'll get into that later. Any other questions? Okay, good. Oh, sorry. Okay, so we move on from a very simple example to a much more complex example. For terminology, we might hear multi-layer perceptron. You might hear artificial neural networks. You might hear feed-forward networks. These all mean the same thing. Since we love analogies to understand what's happening, similar to how the neuron is an analogy for the nodes, I think kids in a trench coat is a good analogy for this multi-layer perceptron. Why do I say this? Because fundamentally, we can break this multi-layer perceptrons into single perceptrons. And from there, because we know how to write single perceptrons, we can write the entire multi-layer perceptron to map that. So each kid would just be our single layer perceptron. Okay, so this is called a 3-layer network with 2 hidden layers. A third layer would be your output. Your 2 hidden layers would be the layers inside there, right here and right here. We'll first look at the input layer. Our input layer, again, is represented by a stack of nodes. It's the first stack of nodes. It represents our raw input, what we're feeding into the network. And the size of it is equal to the number of nodes that's stacked again. Okay. And ideally, each node corresponds to some feature in our data set. Now, just to warm up, what would the size be for this vector? 2. Yeah, okay, cool. Okay, 2 by something, okay? The main thing is that there's a 2 in there. What I mean by batch size, when we feed into our network, our data points, we can either feed in a single point each time. So if we, let's say, take this data point here, we feed it into our network, that'd be a 2 by 1, okay? The main thing is 2. The other dimensions after doesn't really matter. So, x1, x2. But let's say we want to send in like a group of data points, right? There might be 7 data points here, okay? Again, the main thing is that it's 2 by something, 2 by 7. That's why we mean by batch size. Like how many data points are you going to feed into the network? Now, why is this important? We'll talk about that next week. But just keep this in mind. It's 2 by some batch size. Okay, that's our input layer. Our output layer, it represents kind of the objective of the network. So what you want to predict. So for classification, the number of nodes equals to the number of things you're predicting. Okay, and the interpretation is that the final output layer is a probability, okay, of picking that specific thing. And if for regression, the number of nodes equals to the number of dimensions of the output. Okay. So if we want to do multi-classification, let's say we have, instead of 2 classes, we want to classify 8 classes, 9 classes, 10 classes. we use this concept called one-hot encoding, where the vector has all zeros besides a single one somewhere inside the vector, and that one determines the specific class. Okay, what does that mean? What does that look like? So in our example, we have two classes, red and blue. This would mean that, this first node or this first index, we have a 1 there to represent that this is red. And then our second node, if there's a 1 there, this represents that this is blue. Okay. So if we want to classify, let's say, our MNIST data set, how many unique one-hot encoded vectors do we need? And what size should our vector be?
10.
Yeah, 10. Okay. Because there are 10 digits, we want to classify, from 0 to 9. And then that 1 represents a specific class. Okay. Now, since sigmoid function, yeah, 1 represents like the specific class. So like 1, 0, like this vector here, if there's a 1 at the top, that means that, hey, we think this digit is 0. If there's a 1 at the third position, it says, hey, we think this digit is 2. And then you continue going down. So this last one would be like, if there's a 1 there and everything else is 0, then it'd be like, oh, we think this digit is 9. Okay. Okay. Now, sigmoid function doesn't work when we have more than 2 classes. So we have a generalization of the sigmoid function. It's called the softmax function. It's, again, a way to calculate the probability that the input is a specific class. I think that's the way to understand it. Before you input your values into the softmax function, those values are called logits. And they're basically an unnormalized score. And again, this function will be applied element-wise. So just to see what's happening, let's say we have some logits that are 10 and 20. If we apply our softmax function, it computes e to the 10 divided by e to the 10 plus e to the 20, and it gives us the values on the right. That's basically what this mathematical notation is doing. Now, what does this signify? It signifies that we're 99% sure that it's blue, and pretty much 0% sure that the data point we're using is red. Okay. Now we have our hidden layers. I think the best way to understand hidden layers is that it's the layers that process information. It learns how inputs are related to one another. It's where feature mapping occurs. It learns higher level features. I think one thing that's strange is that the number of layers and the number of nodes that you want to create an effective neural network is somewhat arbitrary. It can be as high as 64. It could be as low as 8. It depends on your data set and what you're doing. And then notationally, we represent it by a superscript, which represents the layer that we're at, and a subscript, which represents the node number. So our first stack of nodes here is our first hidden layer, and our second stack is our second hidden layer, because our superscript is 2 and 1. Okay. So again, another way to think about it, back to our spiral example, is that our hidden layer 1 stretches and squeezes it, and our hidden layer 2 continues to stretch and applies nonlinearity until we get a linearly separable data. Yeah.
Who decides how many hidden layers you have?
That is a good question. I would say it's very empirical. You add as many layers as you want until your neural network is effective at separating the data. It could be as small as 2, it could be as big as 100. There's limitations, obviously, but it's really depending on, it's more like you choose a layer, you see how effective the neural network is, and then you go, oh, okay, maybe I need to increase the layer, maybe I need to decrease the layer.
How do you decide the nodes in a layer?
The nodes, I'll talk about later. The layers, I think the intuition is if you have more layers, you have more things to process, more features to extract. The nodes, it's I'll talk about the number of nodes later, but yeah. Now to connect our input layer to our hidden layer or any layer to each other, we have all these like blue lines. All these blue lines are still edges, okay? And the way to understand it is it's just two single perceptrons stacked on each other, right? And notationally, we write that the weights for each, like we have to write down what each weight is. It would be this Ji with L. I omitted the L, but this would be weight 1 because we're connecting to the first hidden layer. And I would be the node number in your current layer, and J would be the node number in your next layer. Okay. So we can separate this into two single perceptrons. I guess I'll give you guys another 2 minutes to write out what H1 of 1 is. You guys can talk amongst yourselves there. So H1 of 1 is the perceptron up top, and H1 of 2 is the perceptron at the bottom. Yeah.
I just wanted to ask, like, is it necessary to use the same observation function for each layer?
Yes. So coming back to that question, thank you for asking. So he asked, is it necessary to choose the same activation function for each layer? I'm not sure, but I believe you do have to use, or at least in PyTorch, they apply the same activation function to the entire stack or the entire layer. But from layer to layer, the activation function might change. So
Oh, yeah, W1, 2, that makes 4.
yes, it should be 2-1. Sorry. Yeah, it should be 2-1. So yeah, again, hidden layer 1 might have an activation function of ReLU, and then hidden layer 2 might have an activation function of 10H. Yeah. All right. Does anyone have an answer for this? What H1 and 1 is in terms of math? Yeah.
Activation function applied to x1 times W11 plus x2 W12 plus whatever bias.
Yeah. So again, we can decompose it into a weighted sum with our activation function wrapped around that weighted sum. So W11 times x1 plus W12 times x2 plus some bias term. Okay. Okay. Yeah.
Yeah, I had a question about the activation function, and because you said that it can be different for each hidden layer. Right?
Yeah.
Is the choice of the function also like an arbitrary / empirical thing, or is there like some method to it?
Good question. Good question. I think typically, I believe you're supposed to pick ReLU first because it's the fastest to compute when training, and then after, if ReLU doesn't work, then you shift to TANH. There are issues that you will when picking like certain activation functions. There are certain qualities that each activation function has, and those qualities may cause some issues. If you know what vanishing gradients are, we'll talk about that next week. That's an issue that will arise with picking a bunch of TANH functions. Yeah. Okay. Now, since we've written out, it's very tedious to write out these equations for every single node. You can think of like a neural network that might have 768 nodes, for example, right? There's no way you're going to write out this equation for every single weight and every single node. So we use this thing called vectorization. I'm not going to, on your own time, you can try these vectorization problems. How I view vectorization, it's very similar to doing derivatives. It's very similar to adding. It's just like, you learn it by practice, okay? Vectorization is a very fast way to compute our weighted sums and our activation functions if we want to compute them, okay? The main thing I want to note here are these vectors, okay, our matrices. Again, we can represent this, our connection from input layer 1 to hidden layer with a weighted sum. This is fundamentally a weighted sum surrounded by our activation function, okay? We're doing this for every single node and the connection to it, every single node in front of us. That's fundamentally what we're doing, okay? Again, as an analogy to our previous example, we have our weighted sum wrapped around, that's been wrapped around by our activation function. Now, going back to that number of nodes that you should pick, that's really related to your dimension. The reason why I want to talk about dimensions will be apparent later, but for PyTorch, the main thing is to make sure that your dimensions match. Or at least when you're writing these equations as well, you want to make sure that these dimensions match. Okay. Again, you guys can read it. Okay. Now, from input layer 1 to input layer to hidden layer 1, what are the dimensions of our weight matrix? And what is the dimension of our bias matrix? What do we think? What do we think? Or maybe I guess the first question is, what is the dimension of our input layer? Yeah.
W1 is 2 by 2.
Yeah.
B is 2 times 1.
Yeah. Again, it's about dimension matching here. Okay, and then I guess I'll give you guys another 2 minutes to write out the equations for Z2 and H2, and then write out the dimensions for your weights and biases. Okay, what do we think the answer is here? What do we think the answer is here? Yeah.
Yeah, so for Z2,
Yeah.
we'll do W2 Z1
Yeah.
plus B2.
Close. It's not Z2. Not Z2. It's I guess, yeah. When you write out your equation, it would be H1. So when you you're connecting the activations from the previous hidden layer. And Z1 would be your pre-activation. So this would be it. All right. Now, again, this is a lot. So if you had to substitute Z2 into, like, I want a composition of functions is basically what I want. How would you write out H2 in terms of X? The right side is writing H2 in terms of X. Okay. I'll give you guys another 2 minutes. 2 minutes. Yeah.
The activation function of W2 times the activation function of W1 X plus D1.
Yeah.
Plus D2.
Yeah. Okay. Yeah, that's correct. So activation function of W2 times activation function W1 X plus B1 wrapped plus B1 wrapped. All right, now how about Y? What do you think about Y? How do you write Y in terms of X? Yeah.
Softmax of W3
Yeah.
times activation
All of that. Yeah.
plus B2.
Got it. Correct. Okay. What's the main point? Why do I want you guys to see that it's like composition of weight plus activation function, and then you have a composition of weight times activation function, and then a composition of your weighted sum. Why do I want to show you this? Because fundamentally, neural networks are compositions of functions. Okay. That's the big thing. Everything's a function. Okay. And neural networks fundamentally are a composition of functions. And they're a composition of a weighted sum plus a bias that you're wrapped around an activation function. And then you do a weighted sum plus a bias around that activation function. And you repeat that over and over again until you reach the last layer. That's your neural network. Okay. Now, if you had to describe what's happening here, what do we see? What do we see? What is this transformation a composition of? Okay. If you had to write it in terms of weights, activation functions, and X. Or I guess no activation function because we didn't apply an activation function here. How would you write this out? Yeah.
I mean, it's just a composition of a bunch of weights and biases, and you just kind of bash them together.
Yeah, yeah. So even though I have 40 layers, I'm still unable to make this linearly separable. Okay. So I can have 40 weight matrices. I can compose it like this. And at the end, I'd still not be able to linearly separate this. Okay. But what I'm trying to say is without your nonlinear function, you can't map to nonlinear functions. Linear functions can only map to linear functions. Okay. You can only do this scaling. There's no interesting behavior here because there's no nonlinear function. Because you don't have your activation function. You can add an infinite number of weight matrices, and you still be in this stretching state, more or less. Okay. Now, if we look at this data set instead, is there a way to separate this data set in 2 dimensions? Is there a way that we can pull, shrink, so that this data set is linearly separable? What do we think? What do we think? Yeah.
With the linear functions, it's impossible.
Yeah, with linear functions, I mean, even with activation functions, do you think it's possible?
Yeah.
Again, your activation functions are pulling. I guess if you were, let's say you have this like Play-Doh like material where you can pull and stretch however you like. Okay, you can't make any cuts. You can only move this on a two-dimensional surface.
Increase the dimension.
Okay, yeah. So to answer your question, the reason why we need more nodes is because there's no way to make this. You can't stretch it into 2 dimensions. Okay, there's no way to make this linearly separable. And this is like an example. I train, or you can train like a neural network to try and linearly separate this, and you'll see that it all collapses to 1. Okay. So this is why you need 3 nodes instead of 2. So there is like a lower bound of the number of nodes you need to make our neural network able to linearly separate our data. I guess here, what would the weight matrix be? What dimension? Someone else. Keep answering questions. Someone else. Oh, okay. Yeah.
So what will be the significant effect of like more nodes?
Okay, yeah. Generally speaking, if you increase the number of nodes, how would I say this? It depends on your like use case, but if you do like object detection,
What in this specific case, what if I use 5?
5 nodes. Good question. Good question. These are good questions. I am not sure. I'm not sure. My guess would be, yeah, I'm not sure. It's still effective if you increase. Like I've tried training it on like 128 nodes, and it's still very effective. I would just say that it's projected to a higher dimensional space. That's why. Can't say. I can't say.
Trying to extract more features at a certain point, there's diminishing returns to add nodes. Because
Yeah.
at some point, you just have like an extra feature that you aren't like looking at an extra feature. So like in this case, if you go to the last one, it makes sense to expand it to like 3 dimensions, like the little circle within the donut. But then it doesn't make sense to keep expanding it because at some point you're already able to linearly separate. It doesn't make sense to add a second layer or extra nodes because you're not extracting any.
Yeah, I understand. So what I'm asking is like, what is the net effect of ID for after the point?
It's more computationally complex.
So like no net effect material.
I mean, beyond computation, I don't think there is.
Yeah, I'm pretty sure. I mean, when you train, I guess when you write these neural networks, the whole point is, if you increase the number of nodes, you're going to have to increase your computation, I guess, cost, right? And so what we want is a neural network that's small as possible that can be able to separate it. Yeah, I'm pretty sure there's no.
Also because of overfitting too, right?
Oh yeah, yeah.
If you have too many nodes, then your model can learn to overfit, and that's why we don't want to try to do too much, make it too big.
Yeah. Yes. But, all right. Yeah.
3 times 2.
Yeah, it is 3 by 2. Okay. The interpretation for different dimensions, I would say, is that if your input dimension is greater than your output dimension, you're compressing the input into a smaller dimension. If it's less than your output dimension, you're projecting it up. So how I'd look at it is we initially have some 2D space. Our hidden layers let us project up to our 3-dimensional space because we have 3 nodes here. And then we're projecting it back down to the 2D space after we've found some linearly separable, or after we've linearly separated the data. Okay. Now, obviously, is everything, 2 dimensions, 3 dimensions? No. Fortunately, we need more dimensions for other data sets. So we go back to our MNIST data set. We want to classify a bunch of digits, okay? And it's a 28 by 28 matrix, I would say, okay? Where each value is a grayscale number. I guess it should be between 0 and 255, but that's besides the point. So when we have like this kind of image, the point is to have it, or some way, somehow, we want to convert it into a vector so that we can work with it, okay? Now, if someone had to describe what I'm doing here, well, what am I doing here? Again, I would say that this row is here, and this row is down here. I would say the other thing is like each row represents the row of the image, and there's 28 rows by 28 rows. I mean, by 28 columns. So what do you think we're doing to this image here if we're converting it into this long vector where each row is flattened or made into a vector? Well, what do we see? What do we see? What do we see? What do we see? Again, each row is this row. This row is this row. Sure.
I mean, you assign order to each pixel.
Yeah.
And based on that order, just like this, as one dimensional array.
Yeah, yeah.
So which,
So what's happening here, basically, is we're taking each row of this image, we're converting it into such that it's like an entire, like it's a, how do I explain this? I mean, visually, it's like you take that one row, you convert it here, you take that other row, you convert it, and you're stacking it until it's one dimension. Okay, it's just like a very long strip of pixels. That's how I would imagine it. Okay. Now, again, this is what I mean by arbitrary. Let's just say, for example, we have this neural network with 2 hidden layers. The first hidden layer has 20 nodes. Second hidden layer has 6 nodes. Our input dimension is 764. What would our weight matrix be for our second hidden layer? So it'd be this one. There's 20 nodes here and there's 6 nodes here. Dimension.
6 by 20.
Yeah, 6 by 20. And our x is 764 by something. Here, I would just say it's by 1. Okay. And what we're doing here during inference time is we're taking this huge stack, we're putting in here, and at the end, we're trying to figure out whether or not it's 5, 7, or it's neither of them. So what is the hidden layer doing here? If we look at our image, you know, how would you go about trying to process this image and extract important features? And I guess what is the important feature here? How I would kind of think about it. Yeah.
The white pixels.
Yeah, the white pixels are your important features. So you would probably split it up into maybe 3 categories, for example, right? You have this top line, you have this line that connects the top line to the bottom line. Something like this, right? This is the important parts of a 5, if you had to describe it. Now, if we want to further process this image, how would you go about processing this image again? Yeah. Yeah. I guess all the way at the end would be each row. I would just say like you would chunk up each feature even more. So that if you want like this specific feature, okay, now we can cut it up into this feature plus this feature. This entire line can be cut up into like 4 chunks, and then this last line can be split up into like some more chunks. Okay. And what our hidden layers are doing is trying to build these chunks up. So from that entire stack of pixels, we're building, you know, our kind of like mini features that then build up to the important feature, and at the end we're like, oh, this is obviously a 5. That's how I would interpret it. And another example for 7. Okay, so the last hidden layer, right? It's at this final state where it's saying, maybe this this top line exists for our input. Okay, let's see. Oh, it does exist for this input. Okay, let's see if this top line exists for our current input. Oh yeah, it does exist. Okay, let's look at the middle part. Does this like feature for 7 exist within this 5? Oh no, it doesn't. And then this specific node doesn't activate. And the same thing happens for hidden layer 1. Okay, it's like a feature detection, I would say, for each node. And as you continue going through the layers, higher level features are at your final layers, and your initial layers are more of your surface level features. Okay. Now, why should you care? Okay, after all this, I've been yapping for almost an hour already. And why should you care? Okay, you know how to make a neural network. You know the terminology. You know how to write it down in terms of math. You know that's cool and everything. But what's the application here? Yeah. I think the cool part is that neural networks are universal approximators. Okay, they can approximate any continuous function arbitrarily well. When I say neural networks, I mean neural networks with activation function. But now, arbitrarily well, what does that mean? That seems like something I'd write on my LinkedIn post. You know, oh man, I did arbitrarily. You know, I contributed to this. I contributed to this company arbitrarily well. Okay, arbitrarily well means that if we look at this Taylor approximation, again, you can decompose any continuous function with Taylor approximation. You know, locally it's doing pretty well. If we train our neural network, it might do as poorly, or it might do as poorly as the image on the right, or it might perfectly fit the curve. Okay, and it depends on, again, your training regime. And the reason why neural networks are so powerful is because functions describe the world. If you ever get a chance, I would look up Thomas Garrity on YouTube and watch Mathematical Maturity. He's very passionate. I'll do a semi reenactment of his passion. Okay, let's say functions describe the world. Okay, my voice speaking to you, that sound wave that's propagating to your ear, that's described by function. Okay, you being able to see this projector, the light hitting off of this projector back to your eye, that's a function. Okay, this image being displayed on this projector, that's a function. Okay, if we're able to describe and formalize everyday object in terms of some function, our neural networks can approximate that function really, really well. Okay, that's why neural networks are able to convert English to Spanish, or I guess French in this case. It's why we can do object detection with a dog. It's why you can give a neural network another neural network that's not been trained, and then it can train it or output a trained version without training the actual network. They're very powerful. That's what I'm trying to say. Very, very powerful. Okay. At the end, there's some additional resources, as I said. These aren't scams, but I think it's funny to get people to click win $1,000 Amazon gift card, even though it sends you to like articles and videos of like intuition, more or less.
Oh, wait, if you can't, then just raise your hand. And then we have to pay for this. See this? Yeah, it's just like a very verified. Okay. So your account. In which case, so are you okay? Hey, don't have please be open. Raise your hand, please.
I would also run the first themselves.
I just opened. Okay, so I'll assume everyone has the notebook ready, right?
And I'm sure everyone remembers how to run a cell. So yeah, first of all, just run the first one. Yeah, that just installs PyTorch and scikit-learn and matplotlib, which should be the libraries that you're using in this exercise. It'll take a while because they're pretty big packages. Wow.
I think it's just the util.py.
Yeah, the utils.py takes so long to make. Yeah.
It's okay.
Yeah.
Because we made sure to use only 7 years.
Oh, wait, what? Because it blows all.
Yeah, that's what cooked us on the first 3.
Oh,
Was because we tried the other like NVIDIA dependencies and stuff.
yeah. We're not training big things, so.
Yeah.
Okay, is everyone able to run the first cell? Okay. First cell good. First cell good.
I have a star. And then it's.
Yeah.
Basically, what's happening is like the starlings in progress. So like basically,
Oh, he's not.
yeah. So like. Yeah, so basically, the start is in progress. Yeah. When a number pops up, that means that it's so yeah, the one is now displayed, right? That means that everything is run. You'll see this like line at the bottom said download utils up by and the song here that utils up 5%. So now like you can basically yeah, something you have to pick up account. So they kind of yes. Utils.py basically has like an upper function. Yeah, that's all I would say.
Just to do testing.
Yeah,
It's like the standard like on your soul, it's kind of make sure that your phone is like correct. Okay. So that's just verifying that if it's not correct, it goes to Matthew.
Yeah, that's a good explanation. Actually, you might be fine. Because like before, when it showed up, you saw how like the numbers disappeared, but the numbers.
Yeah, so after the first cell,
So
when you run the second cell, it might give you an alert saying that the kernel died. It's completely normal because you have to restart a kernel after you install the packages. So it's completely fine. So next, another package installation. Is everyone done installing packages? Raise your hand if you don't have it set up. Okay, if that's the case, we can proceed to our notebook. So I'm sure that he already went through the neural network fundamentals, and we talked about how you can have layers in a neural network, right? And we also talked about how you can have a different amount of inputs mapped to a different amount of outputs, right? Like for example, Oscar's example, you had two neurons mapping to 3 neurons. Luckily in PyTorch, this is very, very simple. So in this neural network function, if you want to build like one of those linear layers, right? For example, let's say I have 2 neurons. I want to map it to 5 neurons, right? This is all you need to do in PyTorch. Does everyone understand? And then linear, right? And then ReLU, right? We talked about ReLU again. Well, luckily, PyTorch builds in ReLU, so we don't actually have to build the calculations ourselves. And yeah, you can just run this cell. And just for some syntax, who here knows about the init and super syntax here? If you don't, it's fine. So I'll explain what's happening, right? The first half of this cell, it sets up the neural network for you, right? So let's say I want a neural network with 2 layers, right? So you can clearly see there's layer 1, layer 2. And let's say I want my neural network to have a ReLU function between layer 1 and layer 2. This is how you set it up. Is it clear for everyone? Yep. And when you train your network, right, you have to send your input data in and you have to send it forward through a neural network. That is what the forward function is for. So I think it's pretty self-explanatory, right? So when you pass in x as an input, you want to pass it into the first layer, right? So here it's just self dot layer 1x, right? You do the same thing for your ReLU, you do the same thing for layer 2.
Why do we define a class simple and then dot module? What does it mean?
It for PyTorch, it just instantiates a model for you essentially. You don't exactly have to know how it works. It's just something you do every time. The NN.module gives you access to all of those like built-in PyTorch functions. Like for example, like NN.linear, NN.relu, you need to put in NN.module there. So like every time you want to make a model, right? Let's say I'll make my model okay, it's a MacBook. Let's say I want to make it called Oscar, right? I'll still sorry, I'll still use like an module. Is that clear? Okay. So I'll run this. So now it's your turn. Now you can build whatever neural network you want. So I'm gonna give you guys around 3 minutes to just follow the same format and just get familiar with the syntax. Yeah. So just build something similar to this. Yeah. So,
Okay.
yeah.
I was like wondering, like, is there like a specific architecture that they?
No, they don't. They can do whatever they want.
Oh,
It's
okay,
just
good.
because then after that, they need to build something for that data set.
I see. Okay.
Yeah.
Why?
Yeah.
Maybe tell people not to call it simple and then
Oh.
I have.
Yeah. Also, don't call it simple and then call another name. Oh, I have to clear this. Everyone doing fine? So right now you might be thinking, well, what do I actually have to think about when I make these models, right? You'll see later. Later you'll be given a task, and there are actually certain numbers that you have to put in to your class in order for the model to work. Wait, Kaden, are you helping with the Zoom?
Yeah, I'm
Just really quick, and then sounds like the super one. The super just scraps from those.
Yeah, the scraps.
Okay. And also like passes.
getting some media.
Oh wait, you're it's all that.
Yeah.
Okay. Because I was sitting here. Okay. Good.
Have you checked the spec?
I should just count this right now. It's.
Okay, is everyone good? Did everyone just build something using the? It's okay. I'll give you another like minute or so. Should I move forward? Yep.
I think it's probably your the name and it's just something.
Oh, just means you have to rerun the Sorry.
Yeah. I'm very sorry.
Yep.
When you have multi-layer neural network,
Yeah.
do you run like value every layer or just the?
Like, do I?
Do you run like value after each layer?
You should. Yes. besides the final output. Do not run ReLU on the final output.
Make sure that you don't have to.
So I can like type out a sample network of what this could look like. Wait, Oscar, can I just go into GitHub and like get I just want to paste this. I just want to paste.
So just paste. Like, do you want to like go up into your while you like talk about this function?
Oh no, I need this solution.
Wait, try it.
We're on the UTMIST.
Just like easy. Type out solution.
Oh, yeah.
walk through the,
Yeah.
instead of pasting it.
That's fine. I'll do it.
They're like I'm trying to like get you.
No, I have this.
Oh, yeah, I
I have it over here. Yes. Sure. Okay, so I'll actually type out a solution and kind of walk you through how this should normally or how it should be done properly. So, oops. Oh my gosh, what is this now? Oh my gosh, what is this? Right, so at the so in the top half, you always have to do this init. So I'm sure everyone has done it already, right? You just directly copy it from the example I gave above. And then this super init is also something you have to do every time. It is what gives you access to the oops. And the next part is where you actually build your neural network. So let's say I want a one-layer neural network. Yeah. And then dot module. Yes, there is. Sorry, that's a typo. Yep. After that, let's say I want to make a layer, right? So I'll just do the following, and then dot linear, and you have to tell PyTorch specifically how many input features you have, right? Or how many input neurons you have, right? So this would just be in features, oops, equals to 2, and then your output features equals to 8. Now, just a tip, you don't actually have to specify in features and out features. You can just put in 2 or 8, but I actually do this usually so that I can understand it myself, right? It's easier to understand if you type out this way. And of course, between layers, we can do a ReLU function, and this is how you would, not like that. This is how you would initialize a ReLU. Oh my gosh, a ReLU. Everyone good? So everything after that's the same thing, right? Let's say I wanna a second layer with and then dot linear, and then now from Oscar's lesson, right? After the after the first layer, how many output features do we have?
8.
Yep, 8. What does that mean for the input features of the second layer? It needs to be 8, right? Or else your neural network is not going to be connected, right? So this needs to be 8, and which is why I like typing out the in features. Out features, this can still be whatever you want. In the example I had, it was 16. Okay, now let's say I have 16 features here, and I want to do a binary classification. That is, if I want to identify, let's say, if a picture has a dog or not. How many output features do you think I need? Some people say 1, some people say 2. And I want to hear the rationale behind each one. Why would it be 2?
Right, so if you're doing a binary classification, you have either 0 or 1. And so what you want to do is the first output basically tells you how likely it is it's a 0, and second tells you how likely it is it's a 1. And so that's why you need to. If you only have one of them, it's a little bit tough for the machine to like. I mean, you can make it work, I guess, but it'll be a little bit weird.
Yeah, well, yeah, I understand the justification, but usually, yeah.
You can have one and then an activation function to
Yeah.
decide if it's 0 or 1.
Yep, precisely. So you want to avoid the sigmoid, right? Also going for the sigmoid. The whole point of the sigmoid function is so Oscar also talks about logits, right? When you put it through a layer, you get logits. These logits, you can pass it into a sigmoid function to give you something that you can consider a confidence value. So for example, if I want to predict if a picture is a dog or not, let's say 1 is a dog and 0 is not a dog, right? If the machine learning model is very confident that it's a dog, it'll output a value like 0.9. If it's not confident that it's a dog, then it'll output a value like 0.1. Does that make sense for everyone? Any questions? Hi, Oscar.
I would just say often that 2 node 1 is also a valid answer. I mean, as long as you have like a way to make it distinguishable for a certain value in a certain class, and another value in a certain class, that they want.
It's just a general, like, usually to make it easier, it would be like that. But yes, to answer your question, 2 will also work. So is everyone good? Yeah. I put the wrong sign there. Is that fine? Yep. And the forward function, I'm sure everyone has implemented already. The forward function is very self-explanatory. So I don't know why the enter key keeps. Why does the enter key keep doing it? Okay. Oh wait, I forgot to. Okay. So in the forward, the good thing about PyTorch is that you can just say, I'm going to pass this input into each layer. So I can just say self dot layer 1 x and so on, right? Okay. Oh my gosh, what is happening? And after that, if I want to put it through relu, I can just do this. Self dot relu x and so on. So does everyone get the general idea here? You just keep doing that until you have exhausted all of your network. Is everyone good? If that's the case, I'm going to move on to the next section.
For that one, do you need the app like a little more random between layer 2 and 3? Like, is it just one?
Very good question. Now, the relu function is the same no matter what, right? The relu function is just 0 on the left, whatever the number is on the right. You do not have to define relu between every layer. So I should actually demonstrate this, right? Let's say I apply the relu here, and let's say I put this number into the second layer, right? So self dot layer 2 x. Oh my gosh. Here, you can just use the same relu, right? Reason being, like I said again, relu is the same. It does the same thing to your input every single time. Good. So this would just be self dot. Oh my gosh, self dot relu x. I'm so sorry about that. I don't know why that's happening. But yeah. And I think in the example we have a tanh, yeah. Self dots and then dot. And if you want to call a tanh function on that x, you do the same thing. So return self dot tanh x. Is everyone clear on how to build a, I guess, like neural network module? Hi.
I'm guessing this we're building everything from scratch, but in reality, we wouldn't be able to. We wouldn't be doing all this, right?
This is actually what you will be doing. Behind the scenes, all of the math, PyTorch does it for you.
Well, it's gonna be a way to like just tell, okay, I want this amount of layers.
That is how you would do it.
Oh, so you manually gotta do layer by layer.
Yeah. But I think it's going to be better than all the matrix math. You don't have to explicitly write out the matrix math, which is the good thing about PyTorch. Any more questions? Let me check on times. Okay, we're good. So next, we talked about forward propagation. And this exercise is to get you pretty familiar with PyTorch matrix multiplication syntax. So I will give you guys another couple of minutes. Try to implement this function there in the PyTorch code. I actually forgot the add syntax.
Yeah. Well, actually, like you should use the at sign. That's a picture.
Yeah. So for syntax, I'll type out the solution with you here. So the question says that you have to compute the forward pass for one hidden layer, where if you can see in the parameters here, you're gonna pass in the input x, you're gonna put it through the weight 1 and add the bias 1, right? You put a relu on it, and then you put it through the weight 2, add a bias on it, and output and return the output, right? Now you might be asking, how do we do that? How do we actually perform that matrix multiplication? This is where I'm going to teach you the syntax for this. So if I want to perform a matrix multiplication in PyTorch, you will use the at symbol. So for example, this expression seems pretty familiar to us, right? It's just what we saw in these slides, right? You have your weight matrix times your input plus your bias. This is how you would do it in PyTorch if you are to do it manually, right? Is everyone clear? Yeah. And after that, if you want to apply relu, you would just do the following. So you would do f dot relu set 1. Is that clear? Yeah.
Why can't we write x equals the first thing and then x equals f dot rel x?
Yes, you can. I am just writing out intermediate variables to make it, I guess, like more clear to see. Yeah.
And why f dot rel?
You could just do an n dot relu.
And
Wait, no, f dot relu. You in here. You'll need to have defined this first if you want to use relu the way you did before. But since here we're not defining our own neural network, we're just trying to compute this forward pass. We just use it directly from the library. So if you want to use relu directly from the library, you can just do f.relu. Right, the next step, the same thing, right? If we want to multiply it by the second weight matrix, you would take the second weight matrix, you multiply it by whatever you had before, and add the bias. Is that clear? And if you want to, I guess, apply relu one last time, here you go. And then you just return y. Also, ignore this thing here. You can just comment that out. Everyone good? Yeah.
Are we supposed to return both z1 and y?
Nope. So you just have to return the variable that stores your final output. So in the I guess in the solution slides that I'm using, it used a variable to hold each stage of the input and then throughout the neural network and then into the output. But like what one of your colleagues said, you can honestly just do x equals that. Like for example, like I can just do like x equals to this, and then oh my gosh, and then x equals to that, and then so on, and just return x. I can do that as well. Yeah.
The first part where you're making our own.
Yeah, because you're not actually running the neural network. You're just building it, right? We haven't passed any input data into it. But yeah, good questions. Is everyone clear on this? If so, I will move on to the next one. Yep, and if you did it properly, it should say it passes an exercise. The exercise just runs some test code in the background. So next up, we're actually going to make use of our model now. We can actually get to see this model in action. So, is everyone at this part of the code? Just run the first cell. All that does is it makes you don't have to know the details. It just makes a data set that is similar to the circle that we looked at in the slides. So if you run these two slides, sorry, these two cells, these are the data that we have generated. So our task is to build a neural network that is able to classify whether or not, if I'm given a point, is it going to be of class 0 or class 1. So this is just showing the data points we have collected. Sounds good? Okay. Sorry. So I don't know if you've covered it. Have you guys covered training and test splits for machine learning or no? I see nods.
I'm pretty sure we did that last week.
Okay, good. So just a refresher. When you have a set of data, right? You would use some portions to train your machine learning model, but you should reserve a small portion so that you can test your model at the end, right? So these data, it shouldn't be involved in training, right? It's for you to see how good your model is doing after you train it. So since this is covered, I'm not going to go into too much detail. All that code does is it does 80-20 split of the training data. Now, same thing again. I want everyone to try to design neural network to perform this task. I'll give you guys this time 5 minutes to do this. It's going to be a very similar drill as before, but there are some things you'll have to think about, especially when it comes to the input and output features between each layer. And also look back at this data, right? How many input features is on each data point? Yeah. So input features should be 2 on your first layer. And since we are trying to determine whether or not this thing is class 0 or class 1, how many output features should we have at the very end? 1. Now you can just do something very similar to what we did here. Like honestly, if you copy and paste this, it'll be your working model. Now how well it performs, I don't know. That's for you to too. But yeah, keep going at it. Give you guys a couple more minutes, yes. Meanwhile that's happening, I'll just implement what the solution had. So like we always do with neural networks, with PyTorch, you always have to do the init. And we're gonna set up our neural network here. So super dot init. I need a bracket here right now. So then self dot layer 1, like I said before, the input features must be 2, right? So this number has to be 2. You might be asking, what number do I put here? Can anyone give me an answer of what number do I put after 2? Any answers? It can be whatever the heck you want. You can put any number there, as long as after all of your layers, you have one single output feature. So that's one of the many customizations. You look at a lot more customizations later, and you learn about something called hyperparameters later. But this shows you just how much things you can tweak yourself when you build your own machine learning model. Yeah.
Inferring reader is free, or at least more than 2. Like inferring reader that's like more than 2. When we discussed how it's like.
Yeah. So ideally, it should now technically you just put 1 there, right? You can just put 1 there and just call it. But that's not good, right? You want it to be deeper. You want it to learn more features. Right? So yeah, you're thinking it's safe. I'll just continue typing out the solution. So, okay, I need to find a way to solve that ampersand problem and have that like stop popping up in my face. Let's say in my second layer, like I said before, the input size needs to match the output size of the previous layer. So 16. Let's say I want like 32 output features. This will output, right? And let's say my last layer, let's say I'm gonna make my last layer now. The input needs to be 32, and the output needs to be, again, what number should this be? This is my final output layer. 1, yes, thank you. Now, for the output, we want to output either whether or not the data point we have is class 0 or class 1. However, with one output feature, you should try to output a number that indicates how confident it is that is class 1, right? So to do that, like Oscar said in the slide, you would use a sigmoid function. So this is how you would, surprise, it's just S has not sigmoid. And the rest is the exact same thing. So I think it's like nearly the exact same as before. So I can just copy, oh my gosh. I just copy and paste from here. Yeah. Does anyone have any questions about this? About building the network? Because after that, we're gonna train it and we can actually see it in action. Let's see. Everyone good? Yeah. Yeah, the sigmoid basically, okay, so after your layers, right? Correct me if I'm wrong, Oscar.
Yeah.
After your layers, right? You will have some number, right? You don't know what it is. It can be like, 1, 2, 5, -3, whatever, right? In this situation, how are we supposed to interpret this number? Well, we're trying to get the model to tell you whether or not the data point is class 0 or 1. The sigmoid squeezes that value into between 0 and 1. And you can interpret it as the confidence that is class 1. Sounds good? Okay, next step on this loop. If you run this, is everyone able to run it without errors? Okay, good. Oh, sorry. Yeah. What is that? Are you able to run it?
So if you see your life,
You just read it straight up, right?
so.
Yep.
You don't have any. We just
Because when you unslap your agent and the very first thing is function about it. All those days. So it's the 6 hours. Just for sure, right now you're saying, and so. It's all.
Yes, it's in area. Yeah. Okay. Are you able to run the thing? So that works right there. Solution. Oh.
Do we have to secure the room for security?
I don't know where.
Oh, it's because like, I think I said that we'll just for features or something. Because like we don't have access. Actually, no, that's actually really because like
Yes.
because of this so like we have to secure like the I guess like wait, do you want to just go to BA3200 and just like on us hold down like make sure that there's
Can you double check that your implementation is similar to this?
if there's any changes then we would need to
I think it might be something to do with your ReLU function. So ReLU of these brackets. Do you see any discrepancies? Yeah.
See.
Oh, yeah, so it's like some of these things. So if we find
I think, is it something to do with your ReLU function?
I kind of
Try running it now.
which one?
Yeah.
Okay, that's good. If you have, yeah, you have to.
So after this, to the I guess, but okay. We need to put this.
I'm not sure if this if it's necessary.
Or whatever. If you double check that you're going out here, so self covers the but you might have a cases where you don't have a sequence at the end. That's for when you return it, you should probably yourself let's say right. Just return it that way. That might it's like it's possible. Right here. I feel like an issue where like maps like so far different 6 ways like that's in this case we can say at the end you'll see that we do return with self on a single computer to class. Yeah, there as well. You want that working it down to you're also like taking in that you're actually like is it because yeah. Here, let's say there's this here. Oh, this is really you can give it this so we're passing the cells and like error. And there's what's wrong here one like if that all test and it's start. I'll see you later. I'll see you. So okay, so if your code ran properly, if do we want to see how many people's code ran properly? Yeah, how many people were able to get to this part? Where you see, oh, that's pretty good. So the majority did, right?
Who was not able to?
Yeah, who is not able to get to this? Okay. First thing you should do, up at the top left, throw your error as well as the code you ran into the chat bot and see if it can help you. Yeah, so I'll explain what's happening here if you're able to get to run. So I'm sure you guys know what a loss function is, right? The loss function tells you how good the model is doing. So, and you guys know we have a testing data set. So every epoch, we're evaluating the model on the test data set. And this loss just tells you at that iteration how well the model is doing, right? And the accuracy here, right? You can see like when it was training, right? The accuracy is pretty bad, right? It's getting like 50% of the points right. But then somewhere in the middle, it starts to become really, really, really good. That means your model is learning to classify those points correctly. And at the end, you can see here, the accuracy is like 95% for a model. So that's how you know your machine learned. And next step is really, yeah, what's up? Accuracy is getting worse. That means you probably have to tweak some parts of your network. Yeah, what's up?
No.
Oh. So after this, the next cell when you run it, it actually shows you what your model is doing, right? So this incorrect point here, right? The model thinks it actually doesn't show which class it is, but yeah. So like the red region is like what the model thinks is class, I forgot what number, class 0. And the small blue one is what the network thinks is class 1. So any point that lies in like the red region, it's gonna assume it's class 0. If it lies in the blue region, it's gonna think it's class 1. And you can see here that there's kind of an edge case here where it's kind of in between, and the model's like, okay, what the hell is this? I'm just gonna, make my best guess. And it doesn't say which class it belongs to, but yeah.
Bro, I think you just have to scale you. Can I say that? Yeah. I don't mind.
It's probably higher to get personal questions.
Okay, I'll see what the heck is that.
Guys, whose code has run?
Wait, whose hasn't? Whose is not working?
I mean,
It's literally how it failed.
We're running pretty low on time, but the next step we can basically do as homework. So the next step is basically the exact same. It's basically going to be the exact same as the first part, but except the second part is hold on. I don't know. Yep. So the next part is the same thing, except you will be analyzing the MNIST data set. It's going to be the images of handwritten digits, and you need to write a neural network that is able to classify whether or not the picture is the number 0, 1, 2, 3, 4, whatnot. So using that, once again, think about how many input features do I need? How many output features do I need, right? If I'm trying to classify between 0 and 9, how many possibilities of outputs are there? 10, yes. And if the image is 28 by 28, how many input features do I have? I think that's the number. I don't know. I don't know 28 times 28 off the top of my head, but yeah. Same idea. Input features, 28 times 28. Output features is 1.
Yeah.
Should be pretty similar to what you're doing in the first half. Do we fix everything?
yeah, it's just like mostly typos.
Yeah. It's like typos are like additional layers.
Yeah.
Yeah.
This is saying.
Wait, Kaden, should I wrap up? The next part's the exact same, basically. So
Okay, yeah. But yeah, we're wrapping up. I need to show this slide.
oh yeah. Oh, just before we leave, we have one more announcement from the
Yes.
academics of UTMIST.
VP. Okay.
Yeah.
Yeah. Bro, what is this? Where did my slide? Oh yeah. Okay. So, during reading week, we'll be running AI Squared. So what is AI Squared? Basically, it's our annual RL tournament that we host at UTMIST, where you get to build your own AI agents to fight in an Super Smash Bros. / Brawlhalla type environment. So this is just like a sneak peek of a game that we made this year. We've implemented weapons, moving platforms, and all that. And yeah, and this is my friend right now playing against the AI. My friend sucks, and the AI also sucks. He just like jumped up into like the heavens and got smited by something. Anyway, but yeah, like it's a super fun tournament. I really encourage everybody to join, also because you get to learn about RL, which is kind of like the growing field of like AI. I'll just say, like I think like it's probably the most exciting thing in AI that's coming up is RL, that I would argue. But maybe I'm biased because I like RL myself.
Reinforcement learning.
Yeah, reinforcement learning. Yeah. Did I not mention that?
I don't know.
Wait, I might not have mentioned that. That's my bad. Anyway, but yeah, like, if you guys want to participate in this tournament, please sign up. This is the QR code to, I believe, the Luma, where you can sign up for the tournament. And yeah, and I think just to reiterate, it's happening during reading week. Our launch day is the Saturday of reading week, and then it's going to be week long, and we'll have like a finals tournament at the end of reading week on November 2nd on the Sunday.
Is
So yeah.
there a way to sign up as a team?
Oh yeah, so for team signups, we'll be launching that closer to the tournament date. First is mainly just like securing your spot, and then we'll be launching a team sign up form later.
Yeah, so join AI Squared.
Join AI Squared, please.